one technical concepts, that is system modeling, to introduce to you. Just presentation today. I don't have problem solving. I will do it next week. So some questions that will come to exam, some parts that in the final exam is about system modeling, transfer function, equation with relationship between output and input. I will introduce this and doing this problem solving next week. Today, we want to introduce the formula, the concept, the theory, and the big picture of the concept. Okay, so let's see the slides. I have two parts for the slides. So if you see my screen, you can see. Okay. So what is control? A control system. So, in the reality, when we have some process, some plant like a boiler, or a room or elevator, any system, electrical system, mechanical system, we want to control it. When we say we want to control it, it means that we want to do the systems, make the systems work well properly. It doesn't go, for example, high speed, it doesn't go high level, it doesn't go for high temperature. We should control it and adjust the output to this desired point. So we need to put some signals or changing input so that the output is under control. So the way that we do it, we say is controller. Controller is a system that attached to the system to change the output of system based on our demand. In different areas, physiology, economics, hydraulics, electronics, mechanics, chemicals, many systems, we have this tool to have a desired control. For example, for a room, if you want to heat up the room, if we have some very low temperature outside, it's winter, and you want to use heater. So heater is inside or maybe in the system, the building. So based on the temperature, we decide to change the temperature, the volume of the heater, the voltage of the heater. So the mechanism that we do it in the heater parts, we call it a heater controller system. Another concept is open loop and dynamic. Open loop is like, as you see that there is a direct forward path from the input to the output. So there is no any signal back from output to the input. Very directly, as you have a lot of things that we don't use any feedback. For example, if you switch off or switch on the light or AC or your computer, it directly acts. So you don't measure the output and based on the output or the environment temperature or light decides, and then you do by yourself. So directly at the beginning, just switch on the light, for example. So there is no any loop there. Okay, but in the system that based on the temperature, like for example AC has a control system inside. So when the temperature is very low, then it automatically gets off, and it doesn't go down that side. Or a heater in the bathroom, for example, if the temperature is high 100 degree, then the switch automatically will be off, so that it doesn't go up to boil and boil and boil. So for the open system, it's very simple. There is no controller in the open system. It is controlled, but it is manually. Manually, you do the controlling process. But for the other side, we have closed loop. Closed loop means that you get some measurement from the output and get it back to the input and compare to what you want, what you desire. If they are the same, is okay. Then you don't send any signals and it works as it is. No need to increase or decrease. But if there is some change, for example, actual room temperature is going up, and we measure it by some thermocouple and compare with your desire, 1 or 2 degrees, for example, difference, then with this, give this by electronic systems, this difference to the controller. Here's something you should put it here before heater to heat it up or down, maybe cool down, maybe you, it depends on this difference. This difference defines the control signal so that it comes down or up. Okay, that is the real normal, regular working control system. So that is feedback. You see, always we have negative feedback. You see, negative, not positive. The value that you will get it from output should be differenced, should be subtracted from the input. So that is the main thing. But we have positive feedback, but not for control system. For other system electronics, sometimes we need to oscillate. We need to add to the output, and we don't want to control. We want to make another signal. So we may have in reality sometimes positive feedback. But positive feedback is not useful for control system. And dynamic. Dynamic means the behavior of system, in what degree they are acting fast. Some systems are very fast. For example, switch. If you hit the switch, it suddenly, simultaneously, the light turns on. So you don't need to wait for 1 minute or even 1 second. But many systems doesn't behave like this. It takes time. For example, if you open the AC, then you should wait until 1 or 2, maybe 5 minutes for temperature of the room to comes down. So this means that we have some dynamic, some waiting, some transition. Or even elevator, when you press, for example, floor 2. So if you press floor 2, it takes a little time to start, not suddenly jumping like this. Or even when you want to stop, it stops smoothly. So this shows the behavior, internal behavior of systems that has some waiting or some delay. So this kinds of delay means dynamic. So as I mentioned, we need to have a negative feedback for control system. The example that I introduced it here and repeated in these different things to emphasize that the system has a negative feedback, positive and negative. And that is measurement. This measurement is some sensor. If I give you some problem, some questions in the assignment or final exam, and I say the sensor is used there, the sensor is used always in the feedback route here. In the feedback line, you can see the measurement. Measurement is done by a sensor, instrument. So sometimes say transducers. Transducers means some signals, for example, chemical translated or transducer to voltage. And this transformation is called a process that we call it transducer system. Yeah, as I mentioned, in many systems, vehicles, cars, airplanes, we have the control systems. Of course, that the control system depends on the complexity of that machine, devices. The more complicated the system, we need to have more complicated control system. So we have different types of controller. we'll talk about it. One of the subject of this module is to introduce different types of controller, like PID controller that we study here, or P simply just proportional. If you want to know more about this, and there are some online resources to follow, and YouTube, many of these are some samples you can follow. These slides will be available in Moodle, so you can access it and follow these videos to have more information in details to see those systems. So yeah, there are some components in control closed loop control system. So this is the right place of each component of system in a block diagram. So block diagram is the visual representation of a system that you place every component inside the blocks. So in the beginning, we have some inputs here. That inputs is like demand. It should be like output. Some values that should be exactly like output. This is just theory here. This theory. There is nothing here. Just we put some number, something that we adjust the value. For example, if the desired objective of the controller is temperature, we should put the temperature number here. And this should be compared with the feedback that we get from the output. So then we have some error. If there is some error, then based on that error, that difference, error doesn't mean that there is something wrong. It is something good. We know the difference between output and input, and we want to adjust it and make it 0. So based on that value, we design the controller and adjust the controller, and the controller sends some signals to the plant. The plant, it may be a water tank, a boiler, or elevator, or room temperature. So it depends on our demand. So then we fix that. If it's not fixed again, we try again and use another. So these are not manually, these are automatically. So when we say designing controller, it means that we do and we fix, set up the system's components, parameters in controller forever. Not for every time we change the system behaviors. No, the controller is designed fixed to do the process forever. Of course, sometimes we need calibration. There are something maybe fix, something not good work, then we should check it again and test. It's okay. Every maybe 6 months or 1 year or 2 years, we need to calibrate the controller, the systems, to see that the sensors works well. There is no error in measurements. So, but the control, all when we say control, it is automatic control. It's automation. So it's not manual controller. So, but block diagram will be discussed in details later. We have one chapter exactly, and only about block diagram simplification. So if we have more than this blocks, if we have 2, 3 cascaded system, in series, some systems may be placed together. Then how to design the controller? First, we need to simplify. So there are some rules to simplify such a complicated block diagrams, and that will be taught maybe in 2, 3 weeks. Another example that I want to see here, that show you, is that sometimes we need to have some extra work, extra effort for controller. So sometimes the controller doesn't work well. We need to add another component controller. And for example, the system works well, but in the beginning has some oscillations, for example. Or it works well, but always there is some drift, some shift between output and input, constant. So there are some effort that we will talk about. It's about complexity of the controller. Then we have modeling. System modeling means the behavior of system equation. So if I give you this system and you tell me that what is the relationship between output and input, that relation means system model. A very simple way. A mathematical model of a system based on the equations that governs the system, which comes from physics, physical rules, we call it system model. So that is the subject for our chapter, for first chapter. I will show you in the next slides. So when, for example, we have some circuits like this or C, then what is the relationship with output and input? I will do it next week. For very simple from circuits theory. But the concept is this. The relationship between output and input means the system model. Okay, so how to use it, how to find it? By using these rules from physics. So it's electrical system. We have four general equation, one for resistor, one for capacitor, one for inductor, and one for diode. Of course, for diode, since it's not linear, I don't discuss it here. No diode. Diode is a single element electrical component. So the relationship between output and input of each of these elements is given to you. So using these rules from physics, you will find the relationship between output in a system that connected here, like RC or RLC. So it depends on the order of system. So we have first order, second order, different types. So I will discuss it next slide. So how to find it? Yeah, as I mentioned, next week I will show by handwriting step by step. Here is just results. Very easy. You know KVL, KCL? KVL, Kirchhoff voltage law and Kirchhoff current law. So we use these two law from electrical theory. V in, that is for voltage, voltage input equals summation of voltage output plus voltage in between. VR plus V out or VC equal V in. The goal of this equation the derivative is driving this to find output in terms of input, the out in terms of input. So I will show you next week how to do it. So now just give you the result. The out over V in is the relationship between output and input. That is the system model. But in mechanics, we don't study this, just showing you what's going on only. I don't give you such a question in exam or in coursework about mechanics. But just introducing that we have similar system to electrical. As you see that we have mass, spring, and damper system. So the wheel in the car is connected to the body of the car through this system. So that's why you have a very soft car when you drive. If there are some damping, something bump on the road, then you see you feel something, but not that much damping. Okay, so that is because of this device. Spring, we have spring, we have some mass. Of course, mass is from the body of the car. We don't introduce another mass in the car. And the most interesting thing is damper. So these elements, two elements, have their own formula. Formula for Newton, coming from Newton law, inertia, F equals ma. A is acceleration, which is the second derivative of the placement with time, and damping is direct equation, which is damping constant to the velocity. So dv. V is the derivative of x with respect to t, that is the variation of place divided by the deviation of time. And spring F equal kx. So there are three F. So this F should be in balance. So F in is equal to the summation of these. So these should be in balance. So this one plus this F plus this F, there are three F, right? This 3F, this one force comes from spring, one from M and mass, and one from damper. So all together will be F in. So then you can find the relationship between output and what is output, that's input. Output is displacement or place. So you want to control the level or the variation or vibration of the car based on those force. Okay, so the output is always is the variable that you want to control. Okay, the control variable is always output. Okay, so the input depends on what the system is, but the output is very simple. The control variable that you want to control always will be the output of your interest. Okay, that is for the first, not today, or the first half of class. We have another chapter slide now for this chapter. So I will give you these slides also showing this about system modeling, the continuation of that, just a review of this, but for electronic. So let's show the slides. Everything is clear until now? Let's go back to the main page. See that everything is clear. Very good. Okay. So this lecture has been recorded before, so you don't miss anything. No worries. It will be. It is on Google Drive. So for electronic, we have voltage, charge, current, and this law: resistor, capacitor, inductor. These are relationships between voltage, charge, and current. Of course, we don't work with charge of elements. Is not something that we can control. Because this there is no device to measure, charge of a system. The device that we have is only for voltage and current. Voltage and current only, no more. So that's why we don't care about Q. Just use it as an intermediate variable to connect the voltage to the current. So these are coming from physics, mechanics, and electronics, electricity. So these are the table. As I said, the mechanical part, we don't need that. We don't work on the mechanical part like mass, moment of inertia. We don't need this. But for the electrical part, we have it, and also fluid and thermal and chemical. There are some equations for these. But for mechatronic, maybe mechatronic, it is okay. It is good. It's useful. These are those equations. So using these equations, we can find the relationship between output and input. So again, we repeated here this system, F and mass, damper and spring, and we can find the relation. So if you see the relationship between output and input, the output is x, here x, displacement of this mass, this object, and the input is F, the force that we push. For electronic, so it just show you the result here, but next week I will explain by one line to see that how we can derive the equation of output to the input. So in the final exam, I will give you such a system, such a circuit, and ask you find the voltage output in terms of input in time domain and in Laplace domain, another subject that today I talk about it. So you see here, easy, very easy. This is the simplest problem in the electrical circuits for the second order system. So the order of system also is another subject, another concept. The order of system means that how many elements in the systems are saving energy elements, saving energy. If a system has some parts that absorb energy and save it, it makes the systems reliable and it makes systems some delay. For example, here, if we have capacitor, if the capacitor is empty, it takes time to charge up. So it means that we cannot sense the voltage same time, same value here after capacitor. We should wait for a while. So it means that it has some dynamic. It introduced some dynamic. But the current through this resistor doesn't show any delay, doesn't have any delay. Anything that you see here, the current, right after this, you will see immediately that value of voltage or that value of current. So it doesn't make a delay. But C and L, since they are storing, saving, it's like a tank in rooftop. Okay, so you should put water, and that water should be stored there, and then after coming up, then you have something in output from that tank. So the number of these elements determines the order of the system. So here there are two of these elements, storing elements, inductors, one, L, and capacitor. Okay, so the numbers of these exactly is the number of the order of the system. So this will be second order system. But this one is first order system. The first order of the previous lecture, just R and C. I showed you before, last slide, RC or RL. So that, but how about this? Second order or first order stuff from mechanical. In mechanical, spring is something that makes delay. Bumping or damper also a device that makes some compression. So it means that you should wait and makes delay the movement. So it is another types of saving energy system. It's not energy system, it is mechanical. So it absorbs some force, and that means that we have two. So this system is a second order system. Also from differential equation, mathematically, this is second order system. You see, second derivative, d derivative, derivative of the order differentiation. We call it in Arabic mushtaq, yes? Deviation of x with deviation of t, but twice means that the system is second order system. And then finally, a new concept, Laplace transform. I think you have heard of this. Maybe you had it in mathematics, engineering mathematics 2, I think, if you took it before or maybe this semester. Yeah, transformation of time to another domain. We call it Laplace domains, like frequency is Laplace transform. So in mathematics, it will be discussed in details, broad way. But here we just use it. We don't go in that detail and do mathematics of Laplace transform. Mathematics, we skip uh, just the results and the application of Laplace transform. We use it here in this module. So this is another form of representation of the system model. System model means relationship between output and input. If it is in time domain, it is output in terms of input. But in Laplace transformation, it is the ratio of output to input. So output divided by input. So in this direction, vertically, we use Laplace transform. Laplace transform is response of the system from time to Laplace. Laplace domain is like frequency domain. It means the changing. It means change. If the behavior of system is very, very fast, then we add, for example, second or the like this. So there are some rules to confer to conform from conform to conform from time to frequency or to Laplace. So if we have first derivative, so for example dx2, if you remember in that equation we had first derivative. So just remove d derivative and replace it with s. S is the Laplace variable, like t. T is time variable in time domain. S is s variable in Laplace domain. So it's very easy to convert from time to Laplace. Wherever you see d, just replace it with s. If you see d square, replace it with s square. If you see d third cube, you replace it with s cube. Okay, so very, very easy. If you don't have x d2, just as it is. So Laplace transform of x of t is just simply x of s. S is variable, s not the value or parameter. So, and in notation, small x is used in for time domain, capital X, big X used for Laplace domain. So for integration, if you add integration, that function will be divided by s. We have something initial value or initial condition. So to comes from in Laplace time to Laplace, we need some initial value. But we assume that all initial value or initial conditions is set to 0. So if it's 0, then we have that simple conversion from time to Laplace. So then when I say the relationship is expressed in terms of ratio, dividing output by input, then we call this fraction transfer function. Okay? Transfer function is simply defined as the ratio of output to the input in Laplace domain, not in time domain. So first we need to find it in time domain, then we need to convert it to Laplace domain, and then dividing output to input to find the transfer function. One of the parts of the question of simple model system modeling in final exam will be transfer function, how to find transfer function. So next week I will explain it, how to find it by some example, and I will show you by handwriting how to find the transfer function for a second order system. So these are the equation in time domain C x of t. So now to convert to Laplace domain is very easy. So m comes on as it is. D square will be replaced s square. D will be s. X of t will be same as is. Okay, so no need to change anything. So x of t, since there is no derivative, just um, put the same thing. So and replace t with s, of course. Okay, so then the transfer function will be the ratio of x over f, x, not f, x over f, because x is output. So then very easy. So just make factor of x of s here, and then you can find simply the ratio of output to the input. So this is the transfer function, not the first one. The first one is just mathematical calculation. So then you need to reverse it. X of rho. So next week I will give you something about this. So similarly for this also we have this initial equations in time domain. You see I and V of t is expressed in this way. Then I convert it to the Laplace domain by using that rule. Vt will be V of s. D will be s. IR will be same. Ri same. Integration will be divided by s. So if we have integration, you see here the integration. So remove that integration and replace it with 1 over s. 1 over s. Then transfer function will be, again, factorization, make some common factor, here is. Is the factor, and then you can find I over v, or you can find v over I. These are depends on what's your output. So you should look at the output of the system, see that which one is output. Here I is output, so it will be this system. For liquid tank, so this is about mechanical, no need to go in details, just show you that the system is first order system. And this is first order because the power is 1. That will be first order. And finally, standard form. So this is one extra subject. This is not that much important. Just to show you that when we find the transfer function, we should put in a way that each of these coefficient has some value, some physical meaning. Physical, for example, here, 1 over gamma 1 divided by 1 plus tau s. What does it mean physically? Tau is, yes, in mathematics is a number, but in engineering, any number has a meaning. They have some physical meaning, physical interpretation. So this one times constant, time constant. Tau, the coefficient of s, is called time constant. And also this is called gain. This gamma gain. For the second order system, which is 1 or 2 chapters of this module, is all about second order system, because in reality, most of this system behaves like a second order system. So we go through in very details about characteristics of the system in 1 or 2 chapter, in 1 chapter, maybe in 2 sessions. So again, this is a standard form. Let me say standard form, we mean by that, by this s square, the coefficient of the leading term should be 1. So then the other term, zeta and omega n, has this value: gain, damping ratio, natural frequency. So these are just introducing them. Maybe chapter 3 is about second order system. Chapter 2. Yeah, chapter 2 is about second order system, analyzing of the system. I will talk about this omega n and zeta. And also for mechanical system, we have meaning for each of these: omega n, natural frequency, damping ratio, and the gain of system. Okay, that's it for today. I hope everything is clear and you get the concepts. So next week I will solve a question, some problems about system modeling, and I will show you how to find a system model for a second order system, for a first order system, by applying this theorem, time domain equations and Laplace domain. And then I will find the transfer function. Okay, everything is clear?
Okay, Mr. Thank you.
You're welcome. Thank you. Thank you. Okay.
Mr. will be same time at 2 o'clock.
Yes. Yes. Next week. Yeah. 2 p.m. Yes. Yeah. Online. Yeah. Definitely during Ramadan time we have online session only. Okay. All right. Thank you for your attention and see you next week, inshallah.